Excuse me. So, lesson number 1, we're looking at the characteristics of what are called quadratic functions. This entire unit is on quadratic functions, and the basic idea behind a quadratic function is that it's a polynomial function that contains a highest degree of 2, and so therefore it must contain an x squared. And the quadratic function is really a polynomial function, so that the degree of the exponents must be whole numbers. So you will see a degree 2. You may or may not see a degree 1, which would be, just plain x. You may or may not see a degree 0, which would just be a constant. Okay, so you must see an x squared though, otherwise it's not a quadratic. So the quadratic function can be written in basically 3 ways. Okay, and so when we look at these, the first one, kind of your, expanded out, sort of the way we were looking at quadratic functions, in order to, or quadratic equations, or even just quadratic expressions, we call that standard form, right? Ax squared plus bx plus c. The a, b, and c can be any number, any real number. It could be a decimal, could be a fraction, could be integers, could be irrational, really. Except of course a cannot be 0. That's really the only stipulation. The second one, really important one, is called the vertex form, and in today's lesson and in tomorrow's lesson we'll understand why it's called the vertex form, and that's because it tells us where the vertex is. The standard form one, actually, by the way, really doesn't tell us much. This particular form of the equation, the only thing that you really get out of that is when you look at the c value, this is your y-intercept, because it's the value of the function when x is 0. Right? And for any function, when x is 0, you're basically looking on the y-axis. So the only thing that really tells you is where the y-intercept is. So standard form, actually not that useful. What we will do with this form, though, is we will convert it. We will change it into vertex form. The vertex form, important because it tells us where the vertex is. And the vertex, I'll just write it here and we'll explore it later on. The vertex is located at the coordinate given by sort of the p value and the q value. Okay, and as I say, we'll explore that and sort of see where that comes from. And then the last one is called the x-intercept form, or sometimes the factored form. And of course, we've been doing factoring, so we're going to continue to do factoring. And there we see it's the factored form because it tells us where the 2 roots are. Right? In other words, where the 2 x-intercepts are. And again, there may be at most 2, there may be 1, because when we were doing our factoring in the previous unit, sometimes we saw that there's really only 1 factor, it shows up twice, but it's really the same factor. And then actually sometimes there might not be any. And again, we'll get into that as we go through this unit. There's one characteristic though that's actually common to all 3 forms. And that characteristic that's common is this parameter of a. Right, so a is really the only thing that's common to all 3 forms. And as we go throughout this unit, we're going to kind of, hopefully at the end of this unit, you'll be able to go, I know what the a stands for. Right? This is what it represents. This is what it tells me. The c value, okay, we know, represents the y-intercept. The p and q value, we will learn that it represents a certain part of the quadratic function. And the r and the s, they tell us where the 2 x-intercepts are. So we're going to do a lot more exploring of that as we go throughout this unit. So just kind of quickly going through here, we can see that all quadratic functions, okay, so if it's got a term of x squared, will always be of one of these 2 basic shapes. It's kind of a U shape that either opens upward or it opens downward, right? But it's kind of got this smooth curve to it with a lowest point here for the open upward, or a highest point here for opens downward. Then we've just got some examples of quadratic functions, a couple of them written in some different forms. All right, so the y equals is written in sort of that standard form. H of x, the bottom one there, is also written in standard form. G of x, or sorry, G of h, right? G of h, that's our vertex form. And of course, what we can do, hopefully recognizing in terms of work that we've done with polynomials, we can expand this out to make it look like standard form. right? Just square the binomial, distribute the 2 through there, simplify, right? So we're going to look at sort of converting back and forth between those forms. And then f of x there, of course, is our factored form. Yeah. Like what these sort of expressions represent? Sure. So in terms of this is called, this guy here, right, is, we'll call it relation form, right? These 3 here are kind of what we call function notation. So function notation says you've got the letter that sort of represents the name of the function. So the g function, just to differentiate it from the f function or from the h function, or perhaps the g function could be the gravity function, or whatever, right? And so the g of h, so the h says, after this equal sign, you should be on the lookout for a variable called h. And this h variable is the input variable in this relationship. It's the domain variable in this relationship. And because it's a function, remember that each input of h produces only one output for g. That's what makes it a function as opposed to a relation. Because there are other relations where you put a number in and 2 perhaps, or even 3 numbers come out, and it might be different, right? Okay, so g of h simply says that g is the name of the function, h is going to be that domain variable or independent variable, and then here's what we do to the h, right? We subtract 1 from it, we square that result, we multiply that by 2, and then we subtract 3 from it, and you will get a 1, no, I shouldn't say unique, but you'll get 1 g value. And then you plot that ordered pair so that h is like the x value of the function, and then the g of h is like the y value of the function, and then that produces an ordered pair, produces a graph. So it's the same for basically, most of the time we're going to be using something like f of x or g of x or h of x. Can you no. So the excellent point right there. The way you read this is g of h or g at h. What's the value of the g function when h is, right? What's the value of the g function at h equals? And so it's not a product. It's actually a sort of representation that says the value of g when you know what h is. Okay. Because the variables here, g and h, don't represent like specific numbers, so we don't multiply g and h. So it's kind of, it is some terminology and some notation that takes some getting used to, right? And that's why we just introduced it kind of last semester in. Yeah, basically, instead of saying y equals something, you know, with an x in it, this might be, like I say, this could be a specific function. Let's call it the gravity function. The gravity function is dependent upon h. So maybe it represents h height. Well, of course, on planet Earth, gravity is the same. So maybe h represents heliosity, the distance from the sun. That's just a made-up word, but you know. So gravity is dependent upon how close you are to the sun. Right? Gravity on Mercury, for example, is significantly different from gravity on Earth. And so, you know, depending upon what your distance is from the sun, of course, we don't know what that function is, you know, will determine what your gravity is. You know, so typically, like, here's well, we'll see an example as we sort of get to the end of this particular lesson of how that sort of thing works. But function notation, whatever's inside the bracket, that's your input value. Typically, it's x. And then the f function or g typically then just says, here's your y value, right? Except we don't usually use the term y of x. We usually use the term f of x or g of x. But just, yeah, it represents y. Okay. So we had there 4 examples of quadratic functions. Here we've got sort of 3 examples that are not quadratic. So the first equation here, right, you don't see an exponent of 2. And this does not multiply, even though, because in this example here, you don't see an exponent of 2. But if you were to expand this out, you'd get an x squared. Right here, you don't have an exponent of 2 in this first example. This example here, you say, oh, well, there's an exponent of 2. Yeah, but that square root kind of undoes it, right? And there's a little peculiarity to this, but yeah, it kind of undoes that squaring part. So this will result in not a parabola, so not something that looks like this. And then same thing with the last one here. You might say, hey, there's an x squared, right, on the bottom. But the fact that it's on the bottom, remember, really kind of means that there's a negative exponent to it. And so this also will not result in our parabolic shape. Okay. Excuse me. Now, one of the things for really any kind of function, anytime you're kind of learning a new function, you always want to sort of have a really solid idea of what the basic, or in this particular case, it's called the reference function. Right? What does the basic function look like? So when we're talking about quadratics, right, that basic shape, and when we mean basic, we kind of say, okay, looking at this equation, y equals x squared. Because if the x squared is sort of the key characteristic that makes it a parabola, what does it look like? So here's our reference parabola. Notice it starts at the origin, right? At least that's where that bottom is, okay, at 0, 0. And then from there, you can go 1 unit to the right, 1 unit up to get to the point 1, 1. 2 units to the right, 4 up, right? And then if you went 3 units to the right, you'd go, right? Because the basic idea is it's just the square of a number, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And so that kind of, you know that sort of fact. So you should now be able to sort of recognize how the parabola is shaped. Similarly, on the left-hand side, right, if you go 1 unit to the left, okay, so -1 squared is still +1. -2, when you square -2, you still get +4, et cetera, et cetera. Okay, so that's our, excuse me, that's our basic, excuse me, our basic function, our reference parabola. Okay, and this idea can be useful when it comes to some other work that we're going to do in either lesson number 2 or lesson number 3. Question?
So if it like curves upwards like
yes.
that, are both sides equal?
What do you mean by equal?
So it would have the same coordinates if they were on one axis.
As long as you start at 0, 0. Right, because I heard the term, the same coordinates. So as long as you start at 0, 0, the same coordinates, yes, right, in terms of the y values for both of these. But if the parabola gets moved, so the coordinates themselves actually change, but I think the characteristic that you're looking for is still really the same, and that is, we're going to kind of describe them here. So you're on the right track, absolutely. So, top of the next page. Characteristics of the graphs of quadratic functions written in, so now this is written in vertex form. Okay. Now the reason they call it vertex form is, well, what is the vertex? Well, the vertex is basically that tip of your graph, the turning point. Vertex, in terms of geometry, is oftentimes the corner of something. Right? When we talk about a triangle, has vertices, this, that, and the other. They're really like the corners. So this is kind of like the corner, except it's not sharp, right? It's rounded. So the vertex is the tip of the graph, or the turning point. And the vertex, always written as coordinates, from that equation, that's where that P and Q come from. So this particular form of the equation, very useful, because reading that form of the equation, we can tell exactly where that highest or lowest point is. Okay, so our vertex here, right, our vertex here, if it opens downward. And so here we've got sort of 3 graphs we can sort of see from the equation, x minus 2 squared plus 1. And it's in the form x minus p. So here, p is equal to 2. So you can see that 2 down at the bottom of the graph. Okay, because it's got to be in the form x minus p. And so here, p is equal to 2. So that's why we can see that it's over where x is equal to 2. And then the q value, okay, whatever numbers afterwards, added or subtracted, that tells us where the q value is, and that tells us the y value of the vertex, which tells us where that highest or lowest point is. Okay, so for this graph, right, we see that the vertex is at 2 and 1. So that tells us that when y is equal to 1, we have what's called a minimum value. In other words, it's the lowest point on this entire parabola, on this entire shape. And it happens when x is equal to 2. Okay? So in other words, kind of going back to that function notation, right? When we substitute an x value of 2 and do our calculation, we get a value of 1. And no matter what other x value we put in there, when we do our calculation, we will always get a result that's higher than 1. Right? In other words, 1 is the lowest that you can get out of that. And then you can see the other two examples here that have, again, the vertex form. So here, this shows x. Question, yeah? Yep. Yep. No, good question. And the answer is no, because the exponent of 2 kind of prevents that. Yeah. So here's an example, right? Like the second one, I think maybe kind of gets to your point. So here, you see the x plus 3, right, inside there is being squared. So if we had to write this as x minus, right, because the form of the vertex form is x minus p, what number would we put there? Well, the answer is, well, we would put negative 3, because the negative 3 here is what makes this x plus 3. Okay. What we can't touch is this negative up front. Okay. We can't pull anything, we can't pull a negative out of the bracket, mostly because there's no negative in front of the x. So we don't want to actually be pulling anything there. So the form of this, vertex form of this equation, x plus 3, actually tells us that our vertex is at negative 3, or at least the x value of the vertex is negative 3. And then again, the plus 4 at the end here tells us what that y value actually is. Okay. Now, the difference between f of x and g of x, besides the numbers, one of them opens up and one of them opens down. Right? The first one opens up, the second one opens down. So besides the numbers, what other sort of thing has changed between those two functions? Max. So the parabola changed kind of direction of opening, right? The first one opens up, the second one opens down. Besides, like I say, besides the numbers, can you look through the equations and say, what else is kind of different? Notice, there's a negative, right? And that negative is out front, right? In front of the term that's going to be squared, right? So in other words, the one that I circled here in red, that negative is actually what makes our parabola open downward. Okay. So looking at our last example, right, here it's f of x is equal to 2 times x plus 2 all squared minus 2. So this one has a positive in front, means it opens up. We'll figure out what that other 2 does. And then our vertex, since it says x plus 2, the x value of our vertex is actually at negative 2. Right, because it's kind of that opposite, right? And then at the end here, you've got a minus 2, and so our y value is minus 2. Basically, yeah, right? For the x one, it's the opposite. For the y one, it's the same. Why is it like that? Well, to answer the question why something is, it's a little more challenging. It's kind of, that's an observation that you've made, right? That it's always the opposite. And then here it's kind of always the same. The reason why it is because when you actually look at the way the parabola moves and what it takes to make it move, that's the way that it takes to make it move. And that we'll get into in the next lesson. Okay, yeah.
So you always grab x and then bring it down. Turn it, bring it down to the equation, but if it's moving downwards, you can like.
You've got a minus sign in front, yeah. Yeah. Okay. Okay. Second characteristic, and this is again, these are really characteristics of every parabola, right? That every parabola has a vertex. Okay, it's just that that particular form of the equation, it's easy to read where that vertex is. One other characteristic about a parabola is you have what's called an axis of symmetry. This kind of goes to Moy's point about, is it equal to the left and to the right? So not going to use the term equal, but it is what we call symmetrical. So that as you move away from the vertex, the rate at which your parabola goes up for each step you go out is the same. Yeah, so that's what we use this term for, is axis of symmetry, or symmetry. The parabola has symmetry to it. So axis of symmetry is technically the vertical line that divides your parabola exactly in half, right? Because it goes through the vertex. That vertex is that lowest point or highest point. So here you can see each of our graphs. We've got this dotted line, kind of dotted purple line, that represents the axis of symmetry. And so that as we move kind of from that vertex point to the left and going up, moving from that vertex point to the right and going up, we're kind of going up at the same rate each time. When we go left, 1 unit, or right 1 unit, it's the same. Okay. So that axis of symmetry, of course, really is described by that p-value. Okay, it's either x plus p, x minus p, or x equals, right? Whatever that p-value of that axis of symmetry is, whatever the p-value of the vertex is. Right? So in this example here, right, there's no equation here. The vertex is at 3 and 1, which means that our equation would be x minus 3 squared. So our axis of symmetry is where x is equal to 3. Right? That's the vertical line. Okay, so it has its own equation, that axis of symmetry, that breaks our parabola into 2 sort of equal pieces. Now, not quite to finish off this equation, okay, because this guy here didn't have an equation. So far we've got the p-value of the vertex. What else can we know from this vertex as to what part of the equation would be? So the other part of the vertex, right? So we've got this axis of symmetry that tells us what's going on inside the bracket. What about the piece afterwards? Right? Plus 1, because that tells us where the y value is of this vertex. Okay. Now, there is an a value that needs to go in front here. Okay, so it's positive because it opens up, right? It's positive because it opens up. Now, look carefully. Is it 1? Thumbs up if you think it's 1. Thumbs down if you think it's not 1. Thumbs sideways if you're not sure. And it's okay to have your thumb sideways. Okay. All right. So we got a good variety. So here's the thing. If a is equal to 1, how should the parabola go as you move a unit left and right, and 2 units left and right, and 3 units left and right? So I'm going to come back to the reference parabola. Right? In the reference parabola, what is our a value? 1, right? Because that would be the coefficient here. So if the a value is 1, then when you go 1 over, you should go 1 up. 2 over, you should go 4 up. 3 over, you should go 9 up. So when you look at this parabola, when you go 1 over, do you go 1 up? No. So our a value is not 1. Right? When you go 2 over, do you go 4 up? No. So the a value is not 1. Okay. So what it is, well, we could figure out later. Okay. That's actually, again, not today's lesson, but at least we know that the a value is, it's not 1. It's positive, but it's not 1. Question or guess? Would it be 6? No. Good guess, though. Okay. Would it be, sorry? 2? Good guess, but no.
Just keep saying numbers.
Just keep saying numbers, yeah. Well, see, here's the thing. Yeah, because a value, at least you make that connection, it has something to do kind of like slope. But the thing is, remember in Math 10C, slope is kind of consistent along a line. Whereas here on a parabola, the slope changes. All right. So a value kind of represents that sort of steepness. Okay. But in terms of the numerical value, we would just be guessing.
Is it 0.5?
Is it 0.5? No. It's close, but it's not.
0.6?
We'll come back to that another day. Anyway, let's keep moving on. Otherwise, we're going to be dragging the whole time. All right, so I think the next characteristic, we've kind of talked about it, that your parabola, again, depending upon which way it opens, okay, all parabolas have an axis of symmetry described by the p-value of the vertex, and then depending upon whether it opens up or down, it either has a minimum or a maximum value. And so here, just quickly, the minimum value, of course, only occurs if the graph opens up. So our a value must be positive. And so in this particular example, we see, our vertex is at 3 and -4. The -4 is the y value. Because our parabola opens upward, we would simply say that the range of our parabola here is y has to be greater than or equal to -4. That lowest point, right, the minimum point here is at y equals -4. And this would describe the range of our function. Question here and then there. Yeah.
Does it have to be like y in the front, or does it?
Typically, you should say y equals. If you're talking about the coordinate, or if you're talking about the minimum value. All right. Now, if it's in a particular context, then what you could say what that is. So it could be height, or it could be gravity, or whatever. Right? Yeah, Max.
So the y coordinate of the vertex.
Yes, absolutely. Right. So that's the q value. Yep. All right. So y equals q is that minimum value if it opens up, or as you see at the bottom of that same page, if it opens downward, then that y equals q is the maximum value. So the question is, what sort of differentiates between whether it's a minimum point or a maximum point? Is simply whether it opens up or down. Right? If it opens up, you have a minimum point. But if it opens down, then you have a maximum point. But it's the same point, right? It's whatever that q value happens to be. Okay, so here, because we've got a negative in front, that's what tells us that it opens downward. Okay, the a value kind of tells us sort of how it will go, but at this point we'll leave it there. Okay, now, so all parabolas have a vertex. So that means all parabolas have an axis of symmetry. All parabolas will have either a maximum or a minimum point. All parabolas will have a y-intercept, because any quadratic function, you can substitute 0 for x. And when you substitute 0, what you're doing is you're evaluating really where that y-intercept is. So of course, here our y-intercept is where it is, and depending upon whatever parabola you may have, your y-intercept will be where it will be. So all parabolas, or all quadratics if you want to describe them, all parabolas have a y-intercept. Excellent question. The answer is no. All right. So in terms of x-intercepts, not all parabolas have an x-intercept or x-intercepts. Okay, so both of, obviously the pictures that you see here do have x-intercepts. So here, x-intercepts, where does it cross the x-axis? And when you have those x-intercepts, okay, notice this last guy here, it says solutions. So that would be the solution to, replacing the y with 0. In other words, it's the solution to the quadratic equation where that quadratic equation would be set equal to 0. Okay, so all parabolas have y-intercepts, but not all parabolas have x-intercepts. Some have one x-intercept, some have two x-intercepts, and some have no x-intercepts. All right, so in general, if you're going to spend 2 minutes studying something, this is what you're studying. The vertex form of the equation, and kind of the pieces of information that it tells you, right? A will tell you whether it opens up or down. If it's positive, it's opening up, which tells you that there's a minimum value. If it's negative, that means it's opening down, tells you that there's a maximum value. The maximum value is found way at the other end of the equation. It's the Q value. And then what's inside the bracket tells you where that axis of symmetry is. And in this form, x minus p, the p value is that axis of symmetry, right? And so it's the opposite kind of what you see, right? If you see x minus 5, then the vertex is at 5, or the axis of symmetry x equals 5. If you see x plus 7, that actually means that the axis of symmetry is at x equals negative 7. It's the opposite. Max.
So the maximum or minimum value is always just one number.
Yes, because it's basically tell me the y value as high as it goes or as low as it goes. Just tell me the number, but it's a y number. Yep.
So for the bracket, do you ever actually square the bracket?
Depends what you want to do with it. If I simply want to look at the equation and say, where's the vertex? I don't touch it. But if I want to take that form of the equation and change it, for example, to find where the x-intercepts are, so then I have to factor it, well then, yes, I need to expand it out first, actually, and then I need to go through the process of factoring. At least that's one of the methods. It's not the only method. So you can expand it out. It just depends what you want to do with it. Okay, so what we're going to do is kind of look at some examples based on the graphs, and then I think over on the next page, we're going to actually use our own calculator to do the same kind of thing. So example number 1 simply says, look at this graph, can we fill in the blanks in terms of where is the vertex? So of course our vertex, it's going to be that turning point. So the coordinate of this particular vertex is negative 3 and 0. Right, so 3 units over to the left, no units up or down. So at this point, in terms of what we can fill in for this equation, since the vertex is at negative 3, our bracket is going to look like x plus 3 all squared. And since the y value of the vertex is 0, we don't bother adding anything at the end of this. Okay, next question, the a value. Positive or negative? That's the easy one, right? Because it opens up. Is the a value 1?
Yes.
Right? So you can visually verify, right? 1 to the left, 1 up. 2 to the left, 4 up. And then 3 to the left or right and 9 up, and it looks pretty close, right? I think that's pretty good. Like that, there's the 9, and I think there's the 4, and there's the 1. So I'm pretty sure that that's our equation right there. Y is equal to x plus 3 all squared. I'm pretty confident that our a value is 1. For sure, it's positive, right? So our axis of symmetry, x is equal to the p value of the vertex, right? X is equal to negative 3. That's our axis of symmetry. That's the vertical line that we would draw that splits our parabola nice and easily into 2 equal parts. Okay, maximum or minimum value? Well, because it opens upward, we should circle the minimum. And the maximum or minimum, or the minimum in this case, is y equals 0. Okay. From this graph, we can tell our x-intercept, there is only one, and it is where x is equal to negative 3, because our vertex point is right on that x-axis. And our y-intercept, well, looks like it's 9, and if we use this equation, it would be 9. And so our y-intercept, y is equal to 9. Now, the easiest question ever in this whole unit, the domain of a quadratic function, any real number, okay? Because this parabola, it has that lowest or highest point, but then it goes off and up to the left forever, off and up to the right forever, or down but it's always going to the left forever. It's always going to the right forever. Because you can take absolutely any number, add or subtract a number, and then square it, and then maybe make it negative or multiply it by something, and then add or subtract another number. So the domain is always any real number. The range, however, is kind of that tricky one. So you have to know where the vertex is, and you have to know which way it opens in order to establish what the range is. So 0 is our vertex point. That's the y value. And so y is going to be compared to 0. And because it opens upward, it says y has got to be greater than or equal to 0. So remember that this is, at least what I've written down so far, is kind of set notation, right? Although even for G, it's not proper IB set notation. We can also use interval notation, right? So the domain from negative infinity to positive infinity, right, goes forever. The range, y is greater than or equal to 0. So 0 is our lowest point. Infinity is our highest point. You always put a rounded bracket on infinity because you can't put your finger on it. But because you can have the equal 0, you put a square bracket on that lower end. Okay, just a little refresher maybe from Math 10C. And so the range is either, it's kind of one direction. You have a lowest or highest number and then off in the other direction. Any questions on that one? Oops, did I go too far? Only one. Okay, so here's another example. We see our vertex. So, if it's clearly identifiable, great, easy to pick off. So our vertex is at 2 and negative 6. And then most of these other things, I don't even have to look at the graph now. Axis of symmetry is where x is equal to 2. The max or min value is where y is equal to negative 6. The only thing to tell the difference is I'd have to know if it opens up or down. So quick look at the graph, it opens up. So that means this is a minimum value. Now, without looking carefully at the graph, the only other two things that we can tell now are domain and range. Domain, easiest question ever. The range, y is going to be compared to that negative 6. And because it opens up, our y is going to be greater than or equal to negative 6. Okay. Now, x-intercept, so for this particular picture, right, they are clearly identified. They've got the dots right on them. So we can see that our x-intercepts are going to be at negative 1 and at positive 5. The y-intercept, a little trickier to find. Okay, again, we'd kind of be guessing that it's, negative 3 and something. So here's again what we'd like to be able to do, and this will be kind of the goal of one of our later lessons is, well, what would the equation be? Can we tell the equation, or at least part of it, in the vertex form? Well, do we have the vertex? Well, yes. So we should be able to kind of go this form. So x plus or minus 2. Right? Because it's moved to the right, it's going to be minus 2. So x minus 2 squared plus or minus 6. Minus 6. Okay? So now the a value. Is a equal to 1? Right? Because you go 1 to the left or 1 to the right, it doesn't go 1 up. Is it greater than or less than 1? Less than 1, right? Because again, what you look for is, as I moved 1 to the right, it doesn't quite go up 1. That means our a value has got to be a little bit less. Any random guesses? 0.8, 2/3. Okay, 0.75. Half. Okay. Okay. So, how are you getting these numbers? Random? Math? What math? Because there is math behind it. Or, I mean, there's a couple of different ways that we could do this. Okay. Oh, it wasn't you. Okay. Michelle. So you use this particular form, right? Okay, so we know that there's an a value in front, all right? And this is actually something that's found in a couple lessons down the road, right? So did you pick one of the x-intercepts here? Yeah. Okay, which one? Positive one or the negative one? Okay, and it doesn't matter which one you pick. But here's what we know. We know that this graph goes through that point. Okay, that point is -1 and 0. In other words, we know that when y is 0 and x is -1, it should satisfy this equation. And if it satisfies that equation, we can use it to determine the a value. Okay, so that's giving lesson number 3. I think it's lesson number 3. That's kind of giving it away. Right? That's what we're going to be doing there. And so that's absolutely one great way to do it. In fact, when you look at lesson, I think it's lesson number 3, that's the only way that they describe it. Okay, but there are other ways that you can determine that that a value ends up being 2/3. Okay, so that's one way. And so if you don't do it, if you don't know how to get that right now, don't worry. By the end of lesson 3, though, then you should worry. So now that we've kind of got this equation, now we could actually substitute, right, to find where these, well, those would be, or to find now where's the y-intercept. So if you substitute 0, 0 minus 2 is -2. -2 squared is +4. 2/3 of +4 would be, and then you got your fraction there, and then you're going to subtract 6. So it's ending up going to be, this guy here is actually at -3 1/3, right? Because you'd have a 2/3 somewhere, but then when you subtract, you're going to end up at -3 1/3. -3 1/3. Or negative, what is that, 10/3. Okay. But without really knowing what that a value is, we would just be estimating. Right? So we want to have a couple of good strategies, and that's exactly one of them, to determine what that a value is. Okay. Now, this, by the way, right, is not the only equation that we could come up with. Because we said that the vertex form is one of them. We could actually, do we have the x-intercepts?
Yeah, that was
And so because we have the 2 x-intercepts, we could actually come up with that factored form as well, in sort of a similar way. Sarah, question? How do we get 2/3? Okay, so this is kind of giving away lesson number 3. We know that this coordinate satisfies this equation. So if we substitute 0 for y, and we substitute -1 for x, and solve this equation, right? You see that we'll solve it for a. So if I, oops, don't forget the square. So if I add 6, right, move that 6 over, and now this is going to be -1 minus 2 is -3. -3 squared is 9. And so to solve for a, you're going to divide both sides by 9. And so that's the algebraic way to get that 2/3. And so now if you miss lesson number 3, this is where it is. Question, Melissa? The 3 1/3? Okay, and is that your question, Mason? Different. Okay, so how we got it now is, well, where is our y-intercept? It occurs when x is 0. And so all we do is solve this, or evaluate this. So 0 minus 2 is -2. Square that is 4. 2/3 of 4 is really 8/3. And 6 is the same as how many thirds? Well, I want to make 6 into an equivalent fraction over 3. Oh, how about 18/3? Right? 18 divided by 3 is 6. And so now 8/3 minus 18/3 is minus 10/3. So that's the minus 10/3, and the 3 1/3 is just the whatever mixed fraction form. right? Like I say, without the A value, we would just be looking here at the y-axis and kind of estimating. So if you said, it's like -3.5, you'd be like, oh, okay. Right? But once we have that, we'd like to be more precise, so we'd like to be able to figure out what those A values are. All right, moving on. Next one. Okay, so again, vertex, we can use our graph and tell that our vertex is at 3 and 2. It means our axis of symmetry is where x is equal to 3. Our max or min value is where y is equal to 2. And sneaking a peek, we see that it opens down. So that's our max value. So of course our domain is any real number. Our range is y compared to -2, and since it's a max value, it opens down. That means our y values must be less than or equal to. Oops, why did I get the negative from? I don't know. It's just +2. No. Well, let's put it this way. There will be instances where we restrict the domain because we have a context. Okay? And we'll see an example later on. But it's still typically any real number, if it's a solid line, most of the time it's a real number between something and something. And just for context. Yeah, pretty much. Right? Especially if it's, like this is a generic function. We don't, have a context to it. So any real number is our domain. Okay. And x-intercepts. So x-intercept, we can see that at least doesn't have the points on it, but it looks pretty clear that our two x-intercepts would be at +2 and +4. Okay. And the A value, okay, two things. Number one is it's negative, right, because it opens down. And if you want to determine what that A value is, you can go through, again, that same process. If you want to do it algebraically, but hopefully, over some time, we'll be able to look at that and kind of say, oh, I can tell what the A value is by looking at the graph, okay, rather than actually doing some algebra work. Okay, so let me see. This question says complete the table given the vertex form, so we can do that. Let's move right into using your calculator. And then I want to do, for sure, I want to get to this one. I want to get to the frog. I want to get to the frog because the frog question now puts it kind of in a context. Okay, so your graphing calculator in this course, this is the unit, probably the first unit where your graphing calculator becomes like essential, okay, critical to your success. So you want to please make sure that you bring yours, have it. And of course you can borrow off of somebody else. During class time, if you don't have a calculator and you have, I think, an Android phone, you can actually get the TI calculator for Android so that you can at least do the work. Then, if you have a computer, there are other ways to get this kind of graphing on your computer. But we want to kind of focus on how does the TI-83 or 84, how does this family of calculators work? So again, on this particular screen, I'm going to make one edit. Okay, so on your graphing calculator, in terms of the window setting, okay, so the window setting is kind of the first thing because you're going to pay attention to this before you press graph, right? Our x values sort of say how wide left and right do we want to go? So smallest number, smallest to largest on x. And then the y's here, smallest to largest on the y's. Really only the first two numbers are critical because they really describe how wide your window will go. The third number, the one that says x SCL or x scale, it basically says this is what the x values are increasing by, what the tick marks represent. So if you leave it as 1, it just means that you're going to probably have a black line if you're kind of zooming out. But you can change it to kind of about 1/10 of whatever the width is that you're wanting to do. And then same thing for the y values. And then this x res, you want to keep this kind of at whatever that smallest, I think it's the smallest number that it basically can go. I think it's at 1. And then that sort of describes how your cursor will move when you sort of are tracing along a graph. Now, the probably the most important menu, I think, is what's called the calculate menu. And so in terms of your calculator, the calc menu is second function and then trace button. So second trace is where you get this calculate menu. And so the calculate menu has a number of good features, has a feature that personally I wouldn't use. So the first one is the value feature, and it lets you find the y-intercept. It actually lets you find the y value for any x value that you tell it. Now, there's actually a shorter way to do this, and that's simply to press trace and then the number. You don't have to come to the calc menu to do that. The second one, it's called the zero feature, and it's used to find the x-intercepts. This is the one that I wouldn't use. Okay? What personally I use instead is I put in a second equation where y2 is equal to 0, and then instead I use the calc intersect feature, which is this number 5, because I don't have to, especially if my parabola is steep, I don't have to have such a hard time kind of doing the above and below. It's more just hit enter 3 times and you will have found one of them. Okay, so yeah, we'll get to them in like the next example. The other two that are really helpful are basically numbers 3 and 4, right? Which allow you to calculate where that maximum or minimum point happens to be. So it will find for you the coordinates of the vertex. Okay. And of course, max or min, you choose it depending upon whether it opens up or down. So if it opens upward, don't choose number 4 because you're finding a maximum. You don't want to find a maximum. If it opens upward, you want to find the minimum. Okay. So let's do that with this example. Okay. Or this example. What have we got? 2. Tell you what, let's either one. Let's do this one. Okay, use your calculator, graph, and fill in the following blanks. So we should be able to actually fill in some of these blanks without graphing it, right? We should be able to see that our vertex there is at -3 and -4. So we should know that our axis of symmetry is x equals -3. Our max or min value will be y is equal to -4. Now, is this a max or a min? I don't have a graph. Min? Min because? How do we know it opens up? I don't see the picture. Positive a value, right? Absolutely. So you get a lot of information, right, from that equation. So positive a value means it opens up, which means we have a minimum value. Our domain, yeah, the easiest one right there. Again, because it's kind of generic. Our range, y is going to be compared to -4. And because it opens up, it's got to be greater than or equal to. Okay. Question, Max? It's simply the x value of that vertex point. Right? So that axis of symmetry, boom, x value of the vertex point. The max or min is the y value of the vertex point. So really, without seeing the graph now, and without wanting to do any algebra, to find the x and y intercepts, now let's plug and play. So go to the y equals, enter our equation. So our equation is 2, open a bracket, x plus 3, close the bracket, squared, -4. So we know that our vertex is at -3, -4. So the standard window is basically where we should almost always start. So you can go zoom 6 to get the standard window. And you see that those x-intercepts, they're not very nice. Right? They're decimals in between. So we need to use our calculator to determine these. Now, before we get there, okay, before we kind of use our calculator, if I'm using this grid here, and if I'm using it with a scale of 1 and 1, my vertex point is at -3 and -4, so that comes down to here. And now, if I want to draw this where can I draw another point? Exactly, right? I can just go, well, what's 1 squared? And then 2 squared. And basically, from here, if I go over 1, do I go up 1? So the a value actually is what tells us no. Instead of going over 1 and up 1, I should go over 1 and up 2. Instead of going over 2 and up 4, I should go over 2 and up 8, right? 2 times, exactly. So 1, 2, 3, 4, 5, 6, 7, 8. And then the nice thing is I only have to kind of do that thing once, and then it's symmetrical from there, right? So our shape, whoops, didn't quite make that. I don't know what's the best way to do this, because I can't see everything. Close. There. And then put arrows on it. All right. So, using our calculator now to find the x and y intercept. So I'm going to find the y-intercept first. So the y-intercept occurs when x is 0. So I can either use the value feature, or I just press the trace button. And the trace button, by default, goes to the middle of your window. Where's the middle of our window? X equals, boom, right? So when you have the standard window, the center is x equals 0. So right away, as soon as I press trace, I see what the y-intercept is. And I can actually plug in now, as I mentioned, when I press trace, if I want to know what's the value when x is equal to 3, I just punch in 3, and there's the y value. All right? I can punch in negative 0.7, and that's the y value. So when x is 0, that's the y-intercept. So the y-intercept is 14. And so the intercepts are the kind of going to be the more challenged question. Good. Okay. So to find the x-intercept, I can either use the 0 feature, or as I mentioned, I think it's easier, it's going to be faster, if I simply put in y2 equals 0. And if you have a one of the colored calculators, okay, then it's easy to tell the difference between red and blue. If you have one of the black and white ones, what you want to do is backspace over to sort of in front of the y2 and press enter once. It will change the style of line from a thinner line to a thicker line, so that when you graph it, you will see the x-axis become bold, right? So that you can tell that you've got the x-axis there. So to find the x-intercept now, I simply use the calc intersect feature, and remember the 3 questions. You should have kind of seen this from Math 10, right? Looking to see where 2 lines cross. Right? Just hit enter 3 times. 1, 2, 3. Because the first time you're just saying is y1 the first line, is y2 the second line, and then the third one is take a guess. So right now, by pressing enter 3 times, we've got one of the x-intercepts highlighted. Okay, so we can see when x is negative 1 point. I wonder if this is a fraction. How on earth could we tell if this is a fraction? Yeah. Okay, so our calculator has done a calculation for us, so it actually stores this value of x. So when I quit, if I push x, you see that's our x value. And so now if we go math, change it to a fraction, oh, maybe not, right? So maybe it's not a fraction value. Or else, maybe it is, and it's just it was rounded. So let's leave it as a decimal. Let's round it to the nearest hundredth. So let's call it negative 1.59. X is equal to negative 1.59. Approximately, let's put the dot on top of there. So it's approximately equal to negative 1.59. And then go and find the other one. So when we press enter just kind of blindly 3 times, we get one of them. All you have to do now is simply recognize that you need to find the other one. So calc intersect, enter, enter. This time I'm just going to take a guess. It's maybe closer to -5. And so I'm just going to punch in there -5. And so then it tells you right away. So you don't actually physically have to move it. You can just enter in a guess value. Yes?
Test with 2x-intercepts you figure out without a calculator.
Yes. It's a long way. We'll get to that later. But the answer is yes. So graphically you will learn, and algebraically you will also learn. So let's call this -4.41. Okay? So that's a way that you can use your calculator to sort of find some different pieces about this parabola. So we've done this particular example. What I want to get to, since we're kind of running a little bit short on time, I want to get to the frog example. And then what I will do is I will write in the answers for that table. And I will write in the answers for example number 2, the one that comes after this, so that when you're kind of doing your homework, you can go online to the website and then look at the notes and look at the examples if you're in any way unsure. Okay? Questions? Good to go? All right. So, question says, a frog sitting on a rock jumps into a pond. The height in centimeters, h in centimeters, of the frog above the surface of the water as a function of time. Okay, so here's where we're using that function notation. H of t, the height is a function of time. So we're expecting a t value in this equation. So there it is. H of t is equal to -490 t squared plus 150 t plus 25. Okay. And of course, what this means is, because it's a function, at any point in time, so you put in one value of time, you're going to get how many values of height? 1, right? That's what makes it a function. For any input value, you get 1 output value, which hopefully makes sense, that at any point in time when you're jumping, you're only at 1 height at one time. So let's enter in our calculator, our equation. In the first one, clear this out. -490, since we don't have, oops, clear that out. -490, we don't have a t, so it's always going to be x. X squared plus 150x plus 25. And I'm going to keep in that second line y equals 0. And it says graph function. So I'm looking at this graph that's here. That gives me a clue as to what the window settings should be. Okay, so the window settings, x, excuse me, goes from 0 up to 0.5 seconds, because obviously frogs are quick. So x, I'm going to go from 0 to 0.5. And if I want mine to be as close to theirs as possible, then for the x scale, I'm going to use 0.05, right? Because I see 0, I see 0.1, I see 0.2, so the other line in between there is 0.05. In terms of the y value, I see that the lowest one that they've got here, because they show it going below a bit, that's okay, is from -10. The highest value looks like it should be 45. And it looks like they've got a line every 5 units. So to get the closest picture to what they have, these are the window settings that we want to use. Question? Go ahead. So I'm just looking at the graph, right? The actual window settings of the graph that they've got there. Okay, so the only one that I really don't care about are the ones where it says the x-res, the delta x, and the trace step. And your calculator might not show that, and that's okay. All right. Yes? So I'm looking at this graph, and that for the time value, the lowest time value is 0. The highest time value is 0.5. So that's my x minimum, my x maximum. And then same thing for the y. The y minimum is -10. The y maximum looks like 45. Those are the two really critical numbers. And then to make the tick marks be in the same spot, I put in the 0.05 and the 5. So again, where are the tick marks going up here? Every 5, yeah. That's what that refers to. Okay? So press graph, and more or less, right, this should look similar to exactly what's in our book.
You didn't put the square.
Probably, right? Especially if you see a straight line. Yeah, you look at your thing, there's no square on the
Ooh.
X. Okay? Anybody else not there? Because we want to make sure everybody's kind of at the same place here. Okay, so coming back now, let's hit the questions. Question number 1, or question A, says, what is the y-intercept? So you could maybe estimate it off the graph. Personally, I would get it from the calculator. And that's simply trace and enter a value of 0. And of course, we could have looked at our equation, because the y-intercept is that constant number on our equation. So the y-intercept is 25. What are the units of our y-intercept? Centimeters. So what does it represent? It represents a height of 25 centimeters, which in the context of the story is what? Yeah, it's the height of the rock, right? Because the frog jumps off of a rock. So what does it represent? The height of the rock. Rocks. The height of the, it says a rock. Frog sitting rock, singular rock. So the height of the rock from which the frog jumps, if you want to be more grammatically correct, from which the frog jumps. Okay, so don't just say that the height's 25 centimeters. And it's definitely not the height of the frog. We don't know how big the frog is, but it's the height of the rock from which he jumps. That's right. Okay, what maximum height does the frog reach? Well, so there's a clue, right, that we want to use our calc feature. And since our parabola opens downward, I mean, the question itself said, what's the maximum height? So select number 4. And then it's going to ask you 3 questions because it doesn't know what your graph looks like. It wants you to sort of, give it a window setting or sort of a left boundary and a right boundary in which it will find this maximum point. So it says the left bound is 0. Is that suitable? In other words, is it clearly to the left of the vertex point?
Yes.
Yes. So we're fine there. Okay, right bound. Well, if I kind of read my scale goes up by 0.05. My right maximum on the window is 0.5. So 0.5, totally legitimate. That's the right end of the window. Take a guess. Okay, well, it looks like about 0.15. Looks like it is about the 3rd tick mark. So you can enter a guess, as long as you enter a number in between there, or move the cursor in between there. What did I punch in? Oh, I punched in 1.5. Whoops. Go to. Yeah, not 1.5, 0.15. That's what I wanted. And there it goes.
36.
Yeah. So now what we have to remember is, what do these 2 numbers tell us? Right? The x value tells us something, and the y value tells us something else. So the question says, what maximum height does the frog reach? Is that 0.15 or is that 36? Right? The maximum is the y value, so it's the 36 point whatever. What do they want? They want to the nearest tenth. So let's call it 36.5. 36.5, that's 36.5 centimeters. When does it reach that height? Well, that's what that x value tells us. And I think we should be more precise than the nearest tenth. I think for when it reaches that height, we should probably use 2 decimal places. So let's call it 0.15 seconds, right? Or even 3 decimals if you want. So 0.15 seconds, right? So that's that calc max. And remember, what does it represent? Okay, so don't just use the trace button and try and trace to that nearest place. Use the calc feature on the calculator. All right, when does the frog hit the surface of the water? How did you find that? Exactly. So when you move the little blinky thing, it gets you close, but it may not actually get the most precise answer. So that's why we use that calc max feature, because then the calculator actually calculates that maximum point. Okay, so that's why when you press trace, like just graph, when you press trace, you get the little spider on it, and then when you move it to the left and to the right, it displays for you the coordinates where it's at. Excuse me. And if all you're doing is kind of saying, oh, wait, 7, 8, oh, no, maybe there, maybe 36.47, but that's just visually, and I can't exactly tell. So that's why we must use the calc feature to find that maximum. Selection number 4. Left boundary. And you can just drag your spider a little bit to the left, drag your spider a little bit to the right for the right bound, take a step, oops. Run away, run away. Yeah. Okay, anyway. So, next question, quickly, we only have a few minutes. When does the frog hit the surface of the water? So it's important to know, well, what are we looking for? X-intercept, that's right. Because the X-intercept says, here's when the height is 0. And of course, this means height above the water. So, are we done with our... Nope, we're not done. So it's still moving. So I'm going to pull up a different one. It's still going. Must be stuck. Something must be stuck. Stuck. Close it. Okay, so for that x-intercept, again, I'm going to put in where y is equal to 0. Negative 490 x squared plus 150x plus 25. Window 0, 0.5, 0.05, 45, 5. Okay. So Y2, remember Y2, at least on one of these black and white calculators, I press enter over here so that it bolds the line. So there's our same frog. And now by having that second line, easier now for me just to use my calc intersect feature to find where that first curve intersects the second curve. And it's close to 0.5, so as long as I hit 0.5, again, I want to make sure at the bottom of the screen that it reads intersection, right? Or maximum or minimum. What am I looking for? I'm looking for the intersection. So 0.42. What did it want? To the nearest hundredth, right? So when does the frog enter the water? We'll call it 0.43 seconds. Yeah, because it says nearest hundred. So we'll call it 0.43. Okay, so we've seen how we use the calc max feature. It's similar for calc min and for finding the x-intercept. Now, so here's an example where in this situation, what's the domain? So it's no longer just any real number. Question, Max.
I use info notation. Can I do hard bracket 0,
Yep.
0.45 hard bracket?
Well, whatever this number is, right? So I would say hard bracket 0 is great because it starts at 0, and then since we are rounding here, 0 or 0.43, yeah, hard bracket's fine. You know, soft bracket would, well, actually probably not be okay on this one because this is what we've rounded that value to. So you can use the interval notation, absolutely fine. What about the range? Okay, so y is less than or equal to 36.5, which is our maximum. Now, here's the question. Does it go below 0?
How do you find the value?
Okay, now, so here's a bit of a kind of a contextual question. The height h is the height above water. When a frog jumps through the air, gravity acts on it in a particular way. When it hits the water, does gravity act on it in the same way? And the answer is no. So that's why, well, basically, that's why for the range here, we have to stop it at 0. Because as soon as it hits the water, this function no longer models its height. There's a different one because the way that the gravity works in the water. So splashdown stops. That's also why we stopped here. In terms of our domain, we stopped when the frog splashed, because then this no longer models that particular situation. Okay, bell's going to ring in like less than a minute. I'm not even sure how much, but the answer to these next two questions: how high is the frog? 0.25 seconds after it jumps. So that's just a trace, 0.25. Because it's the x value, it's the time value. Hit enter, it's 31.9. And then how long is it over 30 meters? This one's a little bit more of a challenge question, a little bit more challenging, but I think you could do it. I'll put up the answer, and then if we need to go through it tomorrow, we will go through it. Okay?